Okay, this is lesson 12 of module 3. This will be the last lesson in module 3 before the end of module assessment. Lesson 13 and 14 we will do after the end of module assessment, and they're not included in it. They're another 2 Pythagorean theorem lessons. So this will be kind of the culmination of what we've learned about similarity. And the title of this lesson is Modeling with Similarity, and modeling just means taking a real world problem and using mathematics to solve it. So we're going to use what we know about similarity and solve some real world problems. Okay, so let's see what the first one is, and you have these in your notes. Okay, so this first example is of a flagpole, and it's a flagpole that is not standing upright. The word for that would be oblique, so it's not at a right angle to the ground, and it's not lying on the ground, so it's slanted. So imagine that there's an oblique flagpole in front of a building. The question is, can we use sunlight and shadows to determine the length of the flagpole? And we're going to assume some information below. There's a diagram here that I would suggest you put some measurements on so that you can begin to model this situation and try to see where you could use the idea of similarity to figure this out. So the length of the shadow of the flagpole is 15 feet. And there's a mark on the flagpole 3 feet from its base. Okay, and presumably we can, whatever this mark is on the flagpole, it casts a shadow that we can see. So the shadow of the 3 foot portion of the flagpole is 1.7 feet. Okay, so what I'd like you to do is just mark up the diagram with what we know and see if you can figure out where there would be similar triangles in this situation, because these will end up being similar triangles. So so think about where the shadow would be, where both shadows would be, and how we could use that to figure out the length of the flagpole, or the height of the flagpole. Actually, it's the length of the flagpole that we want. Okay. All right, so hopefully you've thought about that for a few minutes. You know, a lot of times with problems like this, you think, why can't we just measure it directly? Just climb up the flagpole and measure it. And probably in this case, maybe you could, but there are other cases where this type of technique is used where you would not be able to measure it directly. So if we draw some things on the ground here, we could draw the shadow of the flagpole. So if the sun is, let's get a sun color. If the sun is up here in the sky, and is shining down like so, then we've got a situation where the shadow is going to be coming out this way. So we've got a shadow, not that far probably, but we don't know how far. That's the point. We don't know how tall this is. We do know actually the length of the shadow. The length of our shadow is 15 feet. Okay, and the length of the 3 foot portion, that shadow casts is 1.7 feet. Okay, so that's somewhere in here we could mark the point where the shadow on the smaller part of that is cast. So somewhere right in here, and let's go ahead and give some names to these. So we'll use this O as kind of the point where the flagpole meets the ground. It's kind of like our origin. We'll label this A up at the top of the flagpole. put a point there. And then this could be B right here. And then we have a point on the flagpole. This is our 3-foot mark. And then it casts a shadow also. So we'll say that this point is the shadow, where the shadow is cast there. We'll call this point D. This way we can name all of the ratios. Okay, so you may be saying, all right, I see an angle there, but where's the triangles? And one of these things with shadows, a lot of these problems involving similar triangles involve shadows, and the reason for that is we can assume that all of the sun's rays are coming at a given angle. Okay, that's not a good angle for our situation, but they come at a certain angle at a given time of the day. So at any certain point in time, these rays are going to be cast in a parallel version. So therefore, we can say that AB in our diagram here, AB is parallel to CD. And that's going to be key in solving this problem. Because if the sun's rays are parallel, then we have a situation with similar triangles. So look at this and see if we have enough information to figure out the height or the length of the flagpole that is here. So we're given the lengths of the shadows. Is that enough to figure out the length of the flagpole itself? So you can pause if you want to think about that some more. And I'll go on. Okay, so we know that this is 3 feet. We know that OC, maybe I should get rid of that. We know that the length of OC is 3 feet. We know that the length of OD is 1.7 feet. So its shadow is not quite as, it's about half of the length on the flagpole. And then we know, we don't know OA because that's our height of the flagpole. So let's put that length OA is what we want to figure out. And length OB is 15 feet. Okay, so let's look at that for a minute. Okay, so now that we know these the various lengths on the sides of these triangles, let's think about the fact that because those lines are parallel, we know we have congruent angles in these triangles, and congruent angles in the triangles means that the triangles are similar. So we can use the fact that the ratios of the side lengths are going to be equal. Okay, so for clarity as we're writing this, let's let our length OA, which is what we're trying to find out, be our unknown. So we'll call our unknown X, and we can set up these ratios. So we know that that the ratio of OA to OC is equal to the ratio of OB to OD. Okay, so just substituting numbers in that, I get OA is X, OC is 3 feet, whoops, we'll go with the numbers for now. Then OB is 15 feet, and OD is 1.7 feet. So those are the sides on there, and so that's the ratio we set up. So to solve this, like we did in lesson 11, this is a proportion because it's two ratios set equal to one another, and I can write a new equation by looking at the cross products. Because anytime we have two ratios that are equal, what we know is that let me just here, that the cross products are equal. So x times 1.7 is going to equal 3 times 15. So that gives us a new equation, x times 1.7 is equal to 3 times 15, which is 45. So x is equal to 45 divided by 1.7. So x is approximately, I'm going to use a calculator on this, 26.47, or about 26.5 feet. So I should include feet in my answer. So the length of the flagpole is about 26.5 feet. So it makes sense because the 3-foot portion cast a shadow of 1.7 feet. So a little bit more than half of the length the flagpole was the shadow. And then the flagpole is 26.5 feet. It cast a shadow of 15. So kind of the proportions check out in this situation. Okay, so that's an example of using, you did have to make an assumption about the rays of the sun being parallel to one another, but this actually does work in real life. You can, and I've done this with basketball poles and such, that looking at the shadows, you can actually predict the height of an unknown object. So, okay, let's look at exercise 1. Okay, let's look at exercise 1. Again, we're trying to determine the height of something without having to measure it directly. So it says you want to determine the approximate height of one of the tallest buildings in the city. You are told that if you place a mirror some distance from yourself so that you can see the top of the building in the mirror, then you can indirectly measure the height using similar triangles. So let O be the location of the mirror so that the person shown can see the top of the building. Okay, and if you took 7th grade science last year, you might have studied light and reflection. So you know that these angles are going to be equal. And they're labeled in the diagram as equal. They're 36 degrees each. So the angle of, I think it's the angle of reflection is equal to the angle of incidence. So it's going to bounce off at the same angle off that mirror. So part A asks us to explain why triangle ABO would be similar to triangle STO. So let's think about that for a few minutes and see if we can figure out why it is so. So go ahead and pause the video and think about that for a while on your own, and then we'll come back together. Okay, so maybe you saw that not only do we know that 36-degree angle in this situation, we have another angle that's known, because we're going to assume that the the building and the street there, or the sidewalk, are at right angles, and this person is also at a right angle with the ground. So by angle criterion, we know that those are similar triangles. They are similar. Let's say that. Okay. And it's because we have that 90-degree angle that we can identify there. Okay, let's look at part B. Okay, so part B asks you to label the diagram with the distances given here. So go ahead and work on that, and I will work on it as well. Okay, so here are the values that are given in the problem. It's 1,750 feet from the figure, the person standing there, to the building. The person is 5.3 feet tall. So we've got that, or up to eye level for that person. Eye level is 5.3 feet. And the distance from the figure to the mirror is 7.2 feet. Okay, and so part C asks us to find the distance from the mirror to the building. So that would be from O to T. So it's going to be subtracting. We could find that that's 1,742.8 feet. So I've left feet off my diagram here because it's hard to fit it in on this screen. But I know all the measurements are in feet. Okay, so we are asked, do we have enough information to determine the approximate height of the building? If yes, determine the approximate height. If not, what additional information is needed? So pause the video, think about that, and then we'll go on. So this is very similar to the problems we did in lesson 11 of deciding if we had enough information to solve for an unknown part. Okay. Okay, so one of the things we know, because we do have similar triangles here by the angle criterion, we know that the ratios of corresponding parts of these similar triangles will be equal. So I know that the ratio of, now one of the things we have to figure out is what are the corresponding parts, because this triangle is drawn over here. So really, if we sit it here, like flip it around, it might be easier to see. It needs to be reflected over right here. So, but we can see that this side length corresponds to this side length, the person, the 5.3. And the side length along the bottom here corresponds to this part. And we don't know this measure, but if we did, it would of course correspond to that side of the triangle. Okay, so we can write the ratio. We know that the ratio of the height of the building, or x, to the height of the person, 5.3, is the same as the ratio of the distance from the mirror to the building, which is the 42.8, to 7.2, that part of the triangle. Those are the corresponding sides. So to solve this, I would set the cross products equal. So x times 7.2 is equal to 5.3 times 1,742.8. And solving that equation by dividing by 7.2, I get, let me just do it. I'm going to divide by 7.2 and divide by 7.2, and I'm going to get x equal to, well, approximately equal to because I'm dividing here. So x is approximately 1,283 feet. So that's how tall our building is, 1,283 feet. Okay, there are other ways that we could have set this ratio up. So let's look at one of those. Okay, here's an alternate way we could have set up these ratios. We could have thought, you know, if I have this triangle, this little triangle in here, then I almost think of this as the dilated length. So it would be 1742 to 7.2 over 7.2 should equal x, the enlarged length, over 5.3, the corresponding part on the smaller triangle. So notice though that this is going to lead to the exact same equation when I do the cross products. I'm going to get x times 7.2 is equal to 1742.8 times 5.3. So x would be all of that. I'll just erase this here. All of that divided by 7.2. Okay, so this cancels out. So we're going to get the exact same answer no matter how we write those ratios, because we're just setting the cross products equal. Okay, so we were able to determine the height of a building just by looking at the reflection in a mirror. Okay, this next problem has to do with measuring the distance across a lake indirectly. Okay, so a geologist wants to determine the distance across the widest part of a nearby lake. The geologist marked off specific points around the lake so that line DE would be parallel to line BC. So we've got these points on the lake so that he could have these parallel lines going on. The segment BC is selected specifically because it's the widest part of the lake. The segment DE is selected specifically because it was a short enough distance to easily measure. The geologist sketched the situation as shown below. So part A asks us, has the geologist done enough work so far that we could use similar triangles to help measure the widest part of the lake? Okay, so you can pause and think about that and write down your ideas, and then I'll talk about them. Okay, so the geologist has marked point A here, and point A kind of becomes the center of dilation for our segments DE and BC. So these lines got connected, and then we determined that this was the center of dilation. So because DE and BC are parallel, we will have congruent angles here, and then another pair over here. So we have similar triangles. This large triangle is similar to the small one that's included by angle-angle criterion. Okay, so the triangles are set up. So now we just need some distances. So part B gives us some distances on our diagram. So why don't you pause the video and you can go ahead and label the diagram with those, and then we'll move on. Okay, so I have labeled the diagram with the values that were given in part B. So, find that. I'm going to keep this picture up. But part B says the geologist made the following measurements. The length of segment DE is 5 feet. The length of segment AE is 7 feet, and the length of EC is 15 feet. So that's all recorded there. Does she have enough information to complete the task? If so, determine the length across the widest part of the lake. If not, state what additional information is needed. So pause and think about that if you haven't already, and then we'll see what we can do here. Okay, so by the measurements that she took, we can find the scale factor of this dilation. We already know that it is a dilation, and the 7-foot and 15-foot measurements will help us figure out the scale factor. So my scale factor is going to be the dilated length, 15. Actually, that's not the dilated length. And let's talk about why it is. The dilated length is actually 22 feet. And the original in closer is 7 feet. Okay, because this would be, AC would be this 22-foot section there. So 22 is to 7 as, so instead of just calculating that as a scale factor, I can use it the same way we've been doing in the other problems and just set these ratios equal. So 22 feet on the large triangle is to 7 feet on the small triangle, as our unknown, let's call this x, that we're trying to find out on the large triangle, is to 5 feet. So that's the proportion that we can set up. And we've been doing this, but just in case you're having trouble setting up these proportions, if you just remember that if, so this 22-foot length is the length on the large triangle, and the 7-foot is on the small. When I set up the other ratio, I need to set it up the same way. So I set it up with the large triangle in the numerator and the small triangle in the denominator. If I set it up the other way, I'm going to end up with the same answer. It's going to lead to the same cross product and the same value for x. So I just have to be consistent in how I write the ratios. It doesn't matter what direction I write them in. So what we get here is that 7x is equal to 5 times 22, or 110. And so x is equal to 110 divided by 7, which is approximately 15.7 feet. Can't quite get that on the screen. So 15.7 feet across the widest part of the lake. So that was part B. Part C asks, assume the geologist could only measure a maximum distance of 12 feet. Could she still find the distance across the widest part of the lake? What would need to be done differently? Well, that seems kind of odd, but we can still answer this question even though it's odd. What she would need to set up differently is just to maybe draw this DE segment a little closer to the widest part of the lake, so that she didn't have to measure more than 12 feet that way. So I guess that would be the only thing. But the thing that makes this problem realistic is that it is easier to measure. Of course, measuring across the water is going to be harder than measuring along the land next to the water. So there doesn't seem to be any reason why she couldn't measure more than 15 feet. But that would be one way she could get around that problem if it was a problem. Okay, so that is exercise 2. And let's go ahead and do exercise 3 now. Okay, this next problem is one that I've actually done some estimates of I've had experience with this, so to speak. And that is placing a tree so that it shades a house. Okay, so this tree is going to be planted in the backyard of a house with the hope that one day it will be tall enough to provide shade to cool the house. A sketch of the house, tree, and sun is shown below. Okay, so here's another one where we got the sun's rays coming down, casting shadows. So we see the beginnings of triangles here. And part A asks us what information is needed to determine how tall the tree must be to provide the desired shade. Okay. So go ahead and pause and think about that for a bit, and then come back and I'll talk about it some more. Okay, so our similar triangles are going to share this point as a common point, or this vertex here, and one of them will be where the tree will be growing. The other is this height of the house right here. So we would need to be able to measure the height of the house. This, of course, is going to be our unknown. How tall do we want the tree to be? So that's going to help us make the decision on what tree to buy. We would need to know the length of the shadow cast by the house, which would be right here. And we would also need to know how far from that point we are going to plant the tree. So if we want to plant the tree there, then how far is that from the end of the shadow of the house? So with that information, we end up with similar triangles, because these are parallel lines because they are at right angles to the ground. And so by the angle criterion, we're going to have similar triangles here. By knowing these two distances, by knowing the distance from the tree to the end of the house's shadow, and knowing the length of the shadow, we have we have measurements for a pair of corresponding sides on this triangle. So then we also know this distance here on the house, so that will help us because it will be proportional to this distance, because those would be another pair of corresponding sides on our similar triangles. So with the information given in part B, let's go ahead and set up the proportion that will help us solve for the desired height of the tree. Okay, so by labeling my diagram, I can more easily communicate the ratios that we're going to set equal. So this, once again, is for part B. We've already talked about part A. So length, the height of the house, length AC, the corresponding triangle side to that, to AC, would be BD. So length BD, that ratio would be our scale factor, and so would length OB over OA. No, it wouldn't. I put it backwards. Okay. Let's make sure we get it set up right. So length AC is on my small triangle. So I want to start with length OA and then length OB on that part of the ratio. Okay, so I put the small triangle for both of these ratios. The part that's in the small triangle is in the numerator, AC and OA, and the part that's from the large triangle is in the denominator, and that would be BD and OB. And the ratios are corresponding sides. So let's see what that looks like. So according to part B, the height of the house is AC, and it is 16 feet. So I have this ratio, 16. BD is the height of my tree. That's my unknown. So that's right there, from there. And then OA is the length of the shadow of the house. And my problem says that the distance from the end of the house's shadow to the base of the tree is 53. And that the sun casts a shadow 32 feet long from a point on the top of the house. So that would be OA is the 32 feet that the shadow, that the house casts, the shadow, 32 feet. And OB is the full distance, and that says the distance from the end of the house's shadow to the base of the tree. That would be this distance here. OB is 53 feet. So 16 is to X as 32 is to 53. So I have 32X is equal to 16 times 53. So X is equal to 16 times 53 divided by 32. And that is approximately 26 and a half feet. 26.5 feet for the tree. Okay, so that would be, we would want to pick, if that's where we want to plant a tree, then we would want to pick a tree that would grow about 26 feet tall. Would be expected to do that. Okay, let's look at part C now, and then we'll be done. Okay, so the last part here, C, is wanting us to predict how long it's going to be, how many years until our tree is the height that we want it to be, 26.5 feet. So we're going to assume that the tree grows at a rate of 2.5 feet per year. If the tree is currently 7 feet tall, how many years will it take for the tree to reach the desired height? So go ahead, once again, pause, try to figure this out on your own, and I will work it out here for us. Okay, so the tree is already 7 feet tall, so we would want to subtract 7 feet from the final height that we want our tree. So our tree needs to grow 19.5 feet, and we want to figure out how many years that's going to take. So it grows 2.5 feet every year. So if I have 19.5 feet, and I divide that by 2.5 feet per year, that's going to tell me how many years it's going to take to get to that point. So, it's going to tell me how many 2.5s are in 19.5, which would give me an idea of how many years. And if I do the math on this, it's going to take about 7.8 years to grow to that height. Okay, I want to show you one more thing with this last problem. If you weren't sure what operation to do there, I like always carrying units along. So here's a way you could do that with units. So I'm starting with 19.5 feet, and I want my answer is going to be in years. And so I have this rate right here. 2.5 feet per year relates feet and years. And so all I have to do is to write this as a unit that's going to cancel out. So I want feet, I want to cancel out feet, and I want years to stay. So if I write it like that, feet will cancel out and years will stay. So 2.5 feet per year just means in 1 year, the tree will grow 2.5 feet. So doing the unit analysis makes it clear that division is what I wanted. 2.5 is going to give me my 7.8 years. Okay, so that carrying the units along can help you figure out what to do with what operation to use. Okay, so have fun with this problem set. You might find it kind of challenging because you might not have had a lot of experience with modeling with mathematics, but it is pretty cool when you can solve an actual real-world problem using the math that you've learned about similar triangles. Okay, that is it for lesson 12.